Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA. Probability Analysis. Part 1. Basic Rules of Probability.
In this session, we will discuss a very important subject that's considered by many statisticians as the backbone of statistics. This is the subject of probability. Probability is a fundamental part of our life. We use probability all the time in expressing so many things. Experts in different fields, they rely on probability in many applications, as we will see by examples very shortly. This session is one of 3 or 4 sessions in which we will go over different aspects of probability. We will begin by discussion of the theory of probability, the classic theory of probability. We will then move into the discussion of empirical probability, which is a very important subject, especially in different applications. We will then in later sessions talk about probability distributions. We will talk about discrete variables and the probability distributions used for discrete variables, as well as probability distributions used for continuous variables. And as we will see, that understanding probability will give you a good idea about what statistics is all about. It's relying on past events, looking at patterns and hoping to establish some probability of the chance of things to occur in the future. In that sense, as I said, probability is considered as the foundation or the backbone of statistics. With that, let us begin our first session of probability. Let's go to the slides. Probability in life. As you watch the news every day, you hear forecasters saying that there is a 70% chance of rain tomorrow. That's one way to describe probability of some form. As you plan to enter a new business, an expert in the field tells you about the probability of making a first-year profit in this business is only 0.4, or there is a 40% chance that you will make a profit. Obviously, you will then have to make a decision whether you want to enter this business or not at this very high chance of risk or relatively low chance of making profit. As you take a new course, you may be wondering about the likelihood of passing or failing the course. If you know that 80% of the students pass the course, then that's an 80% chance of you passing the course, provided that your performance will be as good as the 80% of the students. You hear it on health news all the time that a smoker has a much greater chance of getting lung cancer than a non-smoker does. So as you can see, probability is used in many different forms and many different ways in life, and for that we have to address probability, and we have to understand the fundamental concepts of probability. It's very important first that we define some of the common terms that we will use throughout the discussion of the probability subject. The first term is what we call an experiment. It's a very common term that many people use. It's a pre-planned process for the sake of producing data that can reveal the purpose of the process application or meet the objectives of the study in which the experiment is conducted. In the context of probability, when the term experiment is used, it typically indicates a process that can result in only one of many outcomes. So we have to keep in mind that we use the term experiment in probability because we are interested in one of many outcomes and the chance of this outcome to occur. Speaking of outcomes, the next term is an outcome, which is obviously the result of an experiment. And when we discuss or when we talk about outcome, we are talking about a single output or a single outcome of the experiment, as compared to an event, which is a collection of one or more outcomes of an experiment. These are fundamental terms that we have to use all the time in probability: experiment, an outcome, and an event. The other term, which is extremely important, is the so-called sample space. A sample space is all possible outcomes taken together from an experiment. So when we can display all the possible outcomes of an experiment, that is what we will describe as a sample space. Here is, by example, we rolling two dice, and as you can see, there are in this experiment many outcomes that can happen, many events that can possibly occur, and an outcome, for example, may be 1 and 1, meaning the 6 and 3, as you can see here, or 1 and 2, 1 and 3, and so on. Now, if you're looking at an event, that event may be the odd sum or the even sum, which will be 2 and 2 or 2 and 4 and so on. These are all events which, as you can see, they represent collections of outcomes. What you see here in the bottom of the screen is the entire sample space of an experiment of rolling two dice. So that's what we mean by sample space. These are all the possible outcomes. Ways to display events. There are common ways in probability to display events. One of them is the so-called the Venn diagram, and the other is the tree diagram. In the Venn diagram, as you can see here, the S implies the sample space. That is all the possible outcomes. So if we are tossing a coin, for example, all possible outcomes will be head and tail. And you can see that they are represented by circles inside that square or rectangle, which represent the sample space. A tree diagram, on the other hand, is branches describing the progressive change in the experiment. So if the experiment is only tossing a coin, then the two outcomes that can possibly happen are the head and the tail, as you can see here. We will use these later on in many examples. Here is an example. Display the tree diagram of the experiment of tossing a coin twice. Now, tossing a coin twice would involve 4 outcomes. Head and head is one outcome, tail and tail, head and tail, and tail and head. Now, these 4 outcomes are represented by the sample space. So S here represent the sample space, and the set that we are putting all the outcomes in is the set of sample space. Now, in a tree diagram, we start progressively by the first outcome. It can be either a head or a tail. If a head happened, then the next outcome is likely to be, again, a head or tail. If the first toss resulted in a tail, then the next outcome is likely to be a head or tail again. So what we have here is combinations of outcomes leading to events that are HH, the head and head tail and head, and tail and tail. So you can see that the tree diagram has helped us in illustrating or displaying the events as they come. And you can imagine how useful this is if we are talking about a more complex experiment in which perhaps 4 coins or more are being tossed, and we are looking into all the combinations of events. A tree diagram represents a simple display, graphical display that is, of all the outcomes, and at the very end you will see the entire sample space as being the outcome of the tree diagram. It's also important that we understand what we call mutually exclusive events. When events are mutually exclusive, this means that the occurrence of one event results in other events not to occur at the same time. If you are, for example, tossing a coin, then it's either head or tail, and the occurrence of a head will prevent a tail from happening. So we call these mutually exclusive events. When we inspect the items for shipping in a manufacturing environment, the item can be either good or bad. It can pass or fail. And these are all mutually exclusive events. There is also the collectively exhaustive events. Other events that are called collectively exhaustive events imply that at least one of the events must occur when an experiment is conducted. For example, if we're speaking of rolling a dice, then we have 6 possible outcomes, and in any outcome would be either odd or even. So that makes these events collectively exhaustive. Back to fundamentals. What is probability? Well, probability is a numerical index of the likelihood or the chance that a certain event will occur. Typically, it's a value between 0 and 1, which reveals the relative possibility an event will occur. When a probability is 0 or close to 0, this implies that an event is very improbable to occur, or the chance of occurring this event will be very slim or very small. On the other hand, if p equal 1, then there is a high assurance that an event will occur. So these are our extremes. P is 0 is the low probability side, and P is 1 is the maximum or high probability side. It's also very important that we think of probability from the category of probability that we are dealing with. In this regard, conceptually, there are 2 main types of probability: objective probability and subjective probability. Objective probability is typically based on the relative possibility of occurrence of an event, defined either by the classic law of probability or by using empirical means, as we will discuss shortly. Subjective probability, on the other hand, is revealed from personal judgment, expert opinion, some information. It doesn't rely much on data or numbers, but rather on some form of expert opinion, perhaps, or personal judgment, or perhaps a desire or a wishful thinking, such as when a student say that there is a 90% chance that I will pass this test. Maybe this student is relying on her past performance, but there is no guarantee, and there is no data to support that the chance of her passing this particular course is 90%. When people claim that they know something, it gives a very pleasant feeling sometimes, especially if it turns out that they are right. So subjective probability is a common part of probability that's used by many people around the world, and we have to be very careful whether the people that are expressing a chance or probability are relying on data and facts, or they simply expressing personal judgment or expert opinion, or perhaps some information that they know that we don't know. That takes us to objective probability, which is really the core of this session here. Classic probability, or the classic theory of probability, is the foundation for probability. It's very simple, because the classic probability of an event A is determined by the ratio between the number of favorable outcomes M and the total number of possible outcomes N. So it's M over N, and we express it, as you can see here, that PA, or the probability of the event A, is equal to a ratio, or the ratio between the number of favorable outcomes divided by the number of total outcomes, or the total number of outcomes. In tossing a coin, for example, a total outcome is 2, head and tail. So if the interest is the probability of head or the probability of tail, then it will be 1 divided by 2, and it will be 1/2. That is the classic definition of probability. Now we have to also understand that the probability of non-occurrence of the event A, or the complementary probability, is called the probability of failure. So probability of success will be A, probability of failure will be expressed as PA dash, or P not A. In some books, they will use the symbol Q to express the opposite probability. And as you can see here, since the sum of probability is 1, then the probability of not A, or the QA, will be 1 minus PA, or 1 minus M over N, in comparison with the probability A. So we need to understand that. Given the fact that the sum of probability is 1, then if we know the probability of some event to occur, we will know the probability of some event not to occur, which is 1 minus the probability of the occurrence of the event. In summary, classic probability is based on the definition PA, or the probability of A, which is the number of favorable outcomes M divided by the number of outcomes, total number of outcomes N. And any probability will have to be of any value from 0 to 1. It cannot be negative, and it cannot exceed 1. So the minimum is absolute 0, and the maximum is absolute 1. The sum of probabilities in a given experiment is always 1. So these are the 3 basic rules of probability. PA, M over N, probability range from 0 to 1, and the sum of probabilities equal 1. Let's take an example here. In an experiment of rolling a die, find the probability of obtaining an odd number in one roll of a die. Well, we know that if we roll a die, we will have 6 outcomes. 1, 2, 3, 4, 5, 6. So the probability of obtaining an odd number, we need to first observe how many odd numbers we'll have. And these are the 1, the 3, and the 5. So now we have the favorable outcomes are 3, which are the odd numbers. But the total number of possible outcomes is 6. So 3 divided by 6, by the classic definition of probability, will give us the probability of interest. That is M over N equal 3 divided by 6, which would be 1/2. In an experiment of rolling a die, find the probability of obtaining a number less than 4. Now, a number less than 4 can either be 1, 2, and 3. These are the 3 numbers in rolling a die that will be less than 4. And again, these are the favorable outcomes, the outcomes that we are interested in. So if we divide the number of these outcome or favorable outcome by the total number of outcomes, that will give us again the probability of obtaining a number less than 4. And as you can see here, we can either take each one of them individually. We can say 1 over 6 1 over 6 and 1 over 6, and that will give us 3 over 6. Or we can say that since we have 3 outcomes out of 5, then that will be 3 over, out of 6, I'm sorry, that will be 3 over 6, and that will give us 1/2. In the experiment of rolling a pair of ordinary dice, answer the following questions. What is the probability that both dice have the same face? Now, here is the sample space of rolling 2 dice or 1 die twice. And as you can see, we have 36 outcomes. So the number of total outcomes or all possible outcomes is 36. But what we are interested in is the same face. Well, same face would mean 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So we have 6 outcomes or 6 favorable outcomes. If we divide these by the total number of outcomes, which is 36, then that will give us the probability that both dice show the same face. As you can see here, 6 divided by 36, or 0.167, is the probability of the event of interest. Another example, what's the probability that the sum of 4 are rolled for the same experiment, or that both dice come up with a sum of 4? Sum of 4 would mean 1 and 3, 2 and 2, and 3 and 1. And again, these are 3 favorable outcomes out of the 36. So 3 divided by 36 is 1 over 12, or 0.083, which is the probability of interest. In the sample space below, what is the probability of the 2 faces will have different numbers? Now, again, different numbers means 1 and 2, 1 and 3, 2 and 3. Early on, we were able to get the probability of same numbers or same faces: 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So if we know the probability of the 2 faces being the same, we can easily, instead of counting all the events in which we have different faces, we can easily use the complementary probability, or since 6 over 36 is the probability of the 2 faces being equal, so 1 minus 6 over 36, or 1 minus PA, will give us the PA dash, or the probability of 2 faces not to be equal, or the probability of faces being different. We discussed the classic law of probability, and in the classic law of probability, we learned that all possible outcomes are typically well defined, meaning we know the entire sample space. So as a result, the classic law probability, defined as the number of favorable outcomes divided by the total number of outcomes, should give us specific and well-defined values. When we say the chance of head or tail in tossing a coin is 1/2, this is because we have two possible outcomes, and if it is the chance of head or tail, that's 1 over 2. Similarly, when we say that the chance of 1 or 2 or 3 in rolling a die one time, we have 6 outcomes. So that's the total number of outcomes, and the probability of any outcome, 1 or 2 or 3, would be 1 over 6. So we have a well-defined values of the total number of possible outcomes, as well as the number of outcomes of interest. Even when we went to a more complicated experiment, such as rolling dice twice or 3 or 4 times, again we still have a well-defined number of total possible outcomes, and if we know the number of favorable outcomes, then the classic law of probability is very much straightforward. It's a ratio between the number of favorable outcomes divided by the total number of possible outcomes. We also learned that the sum of probability is always 1. We also know that the probability can range from a value of 0, which is the least, to a value of 1, which is the highest probability that one can have. Now we're moving on to another subject, which is the empirical probability. And to just give you an idea about what empirical probability means, we all know that the chance of head or tail in tossing a coin is 1/2. Now, if we place this question a little bit differently, if for example we say that you go in a closed room and toss the coin 100 times, would you actually get 50 times head and the 50 times tail? If that's the case, then that's what we describe as an empirical probability. But we know that doesn't happen. Meaning, if we toss a coin 100 times, we may get a head maybe 45 times and then a tail 55. And then if we repeat the trial many times, we will have different values of head and tail. So it's not going to be exactly 50-50. But it will be close. Indeed, as we will learn very shortly by the law of large numbers, the more trials that you make in your experiment, the closer the empirical probability approach the classic probability. With this brief introduction, let us go and talk about empirical probability via the slides we have. Empirical probability stems from the concept of relative frequency that we discussed earlier. When we discussed the histogram, we very much discussed the empirical probability in an indirect fashion. If you recall, we defined relative frequency as the frequency of class I divided by the total frequency. That was in the session where we discussed the relative frequency distributions. Well, this set the stage for the concept of empirical probability because, again, it's a ratio. It's a ratio of a number of observations in a certain class divided by the total number of observations. So that should sound a little bit familiar because it's very similar to the classic definition of probability. Indeed, we can say that the probability of an event I may be defined as the number of times event I occurred in past divided by the total number of observations. The point to be made here is the relative frequency concept is what leads us to the concept of empirical probability. Unlike the classic probability, which is associated with a well-defined total number of possible outcomes, as I said in the introduction, empirical probability is associated with the total number of possible outcomes that may vary depending on the experiment under consideration and the number of experimental trials attempted. That takes us to a very important law, which is the law of large number. When you repeat trials many times, then you kind of reach a point where the outcomes become more or less the same. That's what we mean by the law of large number. Imagine an experiment of tossing a coin. And here are the first column represent the trials. The second column represent the number of tossing. For example, in the first trial, you toss the coin 10 times. In the second time, you add another 10, so you have 10 and 10, that's 20. Then you add 10, now you have 30. Then you add 10, now you have 40. So you can see here we have a progressive increase in the number of tossings that we make in each trial. Now, if you look at the first trial, it resulted in a 4 head. So it did not exactly result in a 5 head, which by the classic law probability that would be the case. So if only 4 came out in the first trial, then 4 over 10, we have 0.4, not 0.5. Now, when we add another 10 tossing, now we have 20. That did not yield exactly 10, which is the 50-50 by the classic law, but rather 9. So 9 divided by 20, that gives us 0.45. And so on. As we add more tossings, we will see that in the beginning, the values of the probability are not exactly what we expected them to be, which is the 50-50 by the classic law. But as we add more trials and increase the number of trials in the experiments, we will notice that the probability value will approach a stable value, which in this case is the 0.5, which is what we already know from the classic law of probability. If we graphically display that, we will see that in the first few trials, values of the probability may go up and down, but ultimately, and as we increase the number of trials, you can see that the values of probability are stabilized, and we have now a value of 0.5, which reaches the value of the classic probability. In practice, this is very important because quite often you ask someone about the chance of defects or chance of rejects or chance of failure, and they will know it immediately. Let's take an experiment that actually reflects that. A company was asked about its performance in terms of accepted and rejected products per shipment. The director of the company immediately replied by saying, we have about 0.57% rejection rate. Now, how does he come with this up with this number? I mean, 0.57% rejection rate, that is a probability or a number that he knows from some sources. Well, the question is, how did the director come up with this value without performing any experiment to verify the answer? Well, the fact is he must have performed a lot of experiments. Would a small experiment be sufficient to justify this answer? Let's see. Here is what happened. Every time the items are produced, the company ship items. So here is the first shipment, here is the second shipment, and so on. And if the first shipment had 5,000 items, and he found that we have 380 of these are rejected or defective, then dividing the 380 by the 5,000 will give us a value of probability, which is 0.0076. It's a very, very small probability. If you multiply that by 100, it will give us 0.76. Now, in the next shipment, where he had another 5,000, he added to the first 5, and now he's finding that we have total of 815 rejects. 815 divided by 10,000 will give us 0.0082, which will give us a percent of 0.815 rejects or returns, and so on. We add in, every time we have a shipment, we are looking at the total number of items being shipped, and we are looking at the items rejected. And as we do that on shipment to shipment, we are beginning to establish a value of the percent rejects. And as you can see, just like the experiment of tossing a coin, the value of the percent rejects start to stabilize, and that came out to a value of 0.57. And as you can see here, no matter how much we add, the ratio between the items rejected and the total items has stabilized at 0.57, and that is how the director of the company knew right away that the rejection rate is 0.57%. So that came from historical data in which he had to collect a large amount of data or large numbers, and that's what we call the law of large numbers. As you can see here, in the beginning when he had few shipments and a few items, the probability was unstable. In fact, at some point it was 0.75, then 0.8, and the more you add, the more you stabilize, and the more you have a very good idea about what about your average defects or the chance of having rejects in your operation. This is of course provided that there is no major changes in the process have occurred during these experiments. In summary, the law of large number indicate that if an experiment is repeated many times in identical fashion, it's a key issue that it has to be identical fashion. We cannot change the way we do the experiment if we are to see how the law of large numbers apply. All trials have to be identical. In this case, the probability of an event obtained from this experiment and determined by the relative frequency of the event occurrence approaches the actual or the theoretical probability. We've seen it with tossing the coin experiment, and we've seen it with the rejection or rejects items in the company. It's a very important law, so if somebody want to get into an empirical probability that's as close as possible to the theoretical probability, then the large number rule has to prevail, and we have to do so many experiments. It's very important that trials should be independent, meaning that the outcome of one trial should not depend on the outcome of the previous trial. The method used in the experiment should remain unchanged. You cannot changing the type of experiment that you're doing and expect the law of large number to apply. And the conditions surrounding the trials should remain unchanged during the experiment in order for the law of large number to hold. Now we move to another very important subject of probability, which is the relationship between two or more events. Let's start with two events. Going with the Venn diagram, what we see here is two events, A and B. These are represented by two separate circles. When we have two separate circles, this simply means that we have mutually exclusive events. These are two events that do not have coexistence, meaning the two events do not coexist and there is no overlap between the two events. So the union law here would be dealing with A or B. Now let's look at the second case. Here we have a non-mutually exclusive events, meaning that one event can occur while the others or part of the other is occurring, and that's why we have an intersection between the two circles. If we look at the middle part, which is this shaded part here, this is the A and B. And it's very important in this slide that we distinguish between A or B and A and B, because the addition rules of probability will deal with these two specific aspects, the A or B and the A and B. The A and B speaks of coexistence of the two events. The A or B is the chance of either A or B to occur, as we will see by examples very shortly. That takes us to the rule of addition, the A or B rule. The rule is very simple. If we have two events that are looking like that, these are two separate circles, mutually exclusive, the occurrence of one will happen at the no occurrence of the other, then A or B, the probability of either A or B will be simply the probability of A plus the probability of B. Now, if the two events overlap, meaning we're going to have a coexistence of the two events at some point, which is the A and B, then the law will be expanded to accommodate this overlap. In this case, PA or B will be PA plus BB, but we have to subtract this overlapped portion, which is PA and B. Notice the difference between the two rules here. This rule deals with mutually exclusive events. That's why they are simply, the probability is simply expressed by BA plus B, while this one here is dealing with events that can coexist, and as a result, it's the BA or B is the probability of A plus the probability of A minus the probability of A and B. Let's take an example. Using the sample space that's shown below here, suppose that A is the event that the total is 4, and B is the event that the total is 3. And you can see here in the yellow that this is the event of 3, 2 and 1, and 1 and 2. In the green one, we have 3 and 1, 2 and 2, 1 and 3, and these are the events of 4. So now we are talking about two different events. Now, if C is the event that the total is either 3 or 4, then we need to define the outcomes and find the corresponding probability. Well, A, described by a set, is the event of a total of 4. That's 3, 1, 2, 2, and 1, 3. B is the event of 3 that's described by two outcomes, 2 and 1, and 1 and 2. C, which is A or B, will be combining these two events. Is 3 and 1, 2 and 2, 1 and 3, 2, 1, and 1, 2. So the probability of A, given the fact that these are 3 events, 3 divided by the total number of possible outcomes, which is 36, will give us 3 over 36. The probability of B, which is 2 divided by the total number of outcomes, that's 2 over 36. And the probability of C will be, we can count these, 1, 2, 3, 4, 5, and divide 5 by 36. Or, since we are talking about the probability of A or B, it would be simply the probability of A plus the probability of B, or 3 over 36 plus 2 over 36 by the addition law, since the two events are mutually exclusive. A sum of 3 cannot coexist with a sum of 4. Here is another example that most people are familiar with, which is, suppose a card is selected randomly from an ordinary deck of 52 playing cards. What is the probability that the card selected is either a spade or a face card? Now we know that we have 13 spade, but 3 of these 13 spades, we have 3 face cards. So we have a problem here. We have an overlap. We have 3, 6, 9, 15, 9, 12. We have 12 face cards, and we have 13 spade, but out of the 13, we have 3 face cards. So these are two mutually exclusive events. So in order to get PA or B, we have to account for the overlap. So PA, which is the event of spade, that's the entire 13 divided by 52, plus BB, which is the total number of faces we have, which is 12, divided by the total number of outcomes, that's 52. So 12 divided by 52. Now, PA and B, that is spade and face, we have 3 cards, and that's 3 divided by 52. And if we follow the law of addition in this case, it would be as follows. BA or B would be 13 over 52, which is BA, plus 12 over 52, which is BB, minus BA and B, which is 3 over 52, and that will give us the sum or the result of the probability of A or B. What we just discussed is a combination of empirical rules and classic rules, which will lead us to perhaps the real application of probability in the real world. That is the contingency table, which is the cross-frequency tables, and that we will discuss in the next session. We're still on the subject of probability, but we still have few sessions to finish.